Electromagnetic equations. We have something like this for Maxwell theory. But they knew that the sources for these electromagnetic fields are atoms and moving electrons and things, which we know are quantized. And when you quantize those become operators. But then this equation doesn't make sense unless that's an operator too. It was an argument that you really had to quantize the fields as well. The same argument holds when you look at the Einstein tensor is equal to the energy momentum tensor of matter, because all this matter that gives rise to gravity is described by quantum operators. So you expect that there really needs to be an operator indicator on the curvature too, on the metric.
Which is space.
Space, yeah. Which is a very dynamic place, as it turns out. There's a lot going on there other than like complete emptiness. But how to do that has been a problem for
So it's not infinity.
75 years.
Infinities in quantum field theory also.
Yeah, the infinities here are what's called renormalizable. You get exactly two of them. All other infinities you get in quantum electrodynamics, QED, are expressible in terms of two divergent integrals. And those integrals can be absorbed into the two constants of the theory, the mass and the charge, in a process called renormalization. Basically what you do is you say that the mass and charge that we measure are equal to some bare mass and bare charge plus these infinite integrals, where the difference is some finite thing. So you end up replacing those integrals by these known constants. Everything else works out finite. That's if the theory is renormalizable. What it takes to be renormalizable is a lot like what it takes to be a scale invariant, in fact. For gravity, you would really like the action, instead of being the scalar curvature like this, the Einstein-Hilbert action, you'd like some kind of curvature squared thing here. That property would almost certainly ensure renormalizability. But with the Einstein-Hilbert action, it's not renormalizable. You would require an infinite number. You acquire an infinite number of infinities when you start doing the quantum field theory. So there aren't enough constants around to subtract those off. And you wouldn't be making any predictions by the time you did. So that's one problem with quantizing gravity. Another problem with quantizing gravity is the fact that you've got this minus sign in the metric. And the problem of time, as it's called, has to do, I'm fairly sure, with the way you set up commutation relations. If you have the
M's and P's.
Well,
you've got some pi's and q's of some sort, but you're going to get an a to b nu over here, and this minus sign in the metric means that when you start calculating what your Hilbert space, you get ghost states, you get negative norm states. So that sign creeps in unfortunate ways. So these are a couple of the problems that people have run into. There may be more. Now, some of this has been overcome. String theory, to anything anyone has been able to say about it, is a consistent quantum theory which, at low energy, predicts general relativity. So what happens there is that you have you basically have an idealized piece of string moving in 2 dimensions. 10 dimensions.
Yeah.
Sweeping out a 2-dimensional world sheet. They have charges on the end. It may be a closed loop. The closed loops actually end up being spin 2 states when you quantize the string, much like you would quantize a particle. It's not that much different than particle quantization. So you're very confident of the quantization of the string. What happens? I wish I had some notes on this, but the position of the string world sheet has 2 parameters, and you've got some initial position. You've got the velocity times tau, and then to give the full shape of the string, it's a Fourier series, right? There's no surprise that you get some coefficients here with well, something like e to the I and tau sine and x. The form of this depends on your boundary conditions, and there are different boundary conditions you can choose. Those boundary conditions give rise to half a dozen distinct, 5 in fact, distinct string theories, which turn out to be interestingly related to one another. But this is the basic kind of thing you get as your classical solution for the motion of the string. It can have angular momentum. It can be spinning end for end, or a closed one can be looping round and round like this. But now you quantize it. Well, basically everything gets a hat, and you have these different coefficients, a sub n, alpha sub n. You have an infinite number of operators defined by this one string. And this is actually an advantage. There are lots of string states, and they can correspond to different particles. So one type of string with one type of interaction can combine vibrating different ways. The energies are such that a different frequency of mode of vibration of a string can have a vastly different mass and correspond to a whole spectrum of particles. Very different particles, depending on what charges you have on the ends of things. So the thing that happens, and I'd have to look this up to find out exactly how, but you're able to define an operator that is quadratic in these alphas. And then something here and something here, such that you get an anti-symmetric operator here. And you also have this momentum operator here. It turns out that, and this is the reason for 10 dimensions, in 10 dimensions, a certain extra term cancels, and these satisfy the Poincare-Lie algebra. The Poincare-Lie algebra is the starting point, is the fundamental symmetry that leads to general relativity. So, right at this point, when you have that symmetry built into the quantum theory, notice these are quantum operators, but they also satisfy the usual Poincare algebra. And so you expect to get a generally coordinate invariant gravity theory out for those spin 2 modes, and indeed you do. Shirk and Schwartz showed in, I think it was 1976, that in fact, if you do a perturbative expansion of the bosonic modes of the string, and with particular attention to the spin 2 modes, you arrive at the Einstein-Hilbert action for the gravitational sector, for the spin 2 modes. They only did it to linear order, but then subsequently it's been done to cubic order and the curvature. There are corrections. The corrections at quadratic order in the curvature come in with a coefficient that's on the order of the Planck length squared. So it's extremely close to general relativity. And you would only expect to see deviations in extremely strong gravitational situations inside a black hole or Big Bang, very early cosmology. Maybe we'll see echoes of that. But the cubic, the quadratic terms are something that can be handled. This was my dissertation. My dissertation was to find the black hole solutions in this enhanced theory of gravity with these extra quadratic terms in the action. And that's been a very popular paper. But the cubic terms are completely intractable. To find any kind of solution there would be a long piece of work. And have a coefficient that's probably Planck length cubed or something, or Planck length to the, some even larger power. Okay, so string theory holds a great promise for, yes, including in our quantum field theory, the effect of gravitons, the exchange of gravitational quanta, along with the exchange of other kinds of quanta of the standard model. The trick now with string theory is to understand how that 10-dimensional theory manifests as 4 macroscopic dimensions, quite possibly with the remaining 6 compactified to some small scale, possibly some other sort of compactification that some of us are actually looking at. But that's sort of where getting the standard model out of string theory stands, as getting that connection between 10 and 4 dimensions. But, okay, long answer to a short question, but it's a good question. And certainly, yes, we would like to see general relativity or something very close to it handled in the same way that we deal with other quantum field theories, the other known interactions, the strong interaction and the electroweak interaction.
Quick question, and
Yeah.
I think the answer will be given in your office hours, but
Okay.
but I want to say it that way I don't forget.
Yeah.
So this bifurcation that we have in biconformal space, where you have the momentum, what we used to call the momentum term. I don't know what it is.
Well, in the generic case, it actually is. It is the cotangent space. It is the momentum space
Okay.
of a relativistic phase space.
Right.
But
And then these
in a special case, it's something else.
Right. Okay. Did that exist if you looked at very high energies, let's say, that existed in the early universe? Would that separation have existed? Or could we comment meaningfully about that at this stage?
Yeah, I would say yes, that would exist. Though, okay, so it helps to discuss a particular scenario. For those of you who may not be familiar with biconformal space, this is a conformal gauge theory of gravity that we've shown reduces to general relativity, but it describes a relativistic phase space. So as it describes general relativity, it really starts out as an 8-dimensional space, not 4. And what one could do is write a 10-dimensional version of this that would describe 5-dimensional general relativity, and compactify just 1 dimension of the space-time and have general relativity without worrying about 6-dimensional compactifications. So there would be some real advantages to such a theory. The question is, what happens at high energy? In general, this model, you would recover a 10-dimensional biconformal space. So it would be 5-dimensional gravity. It would be like a 5D Kaluza-Klein, the original Kaluza-Klein maybe, where instead of that circle basically opens out.
Because right now we have a curvature and it has different components, and those components don't mix. So you have like the portion, you have...
The symmetry of the bundle is what separates those different pieces.
Oh!
That's just from the conformal symmetry that you get that.
Okay, I felt maybe that gets mixed up at high energies. Okay.
But yeah, you would, anything you compactify would decompactify at high enough energy. But other than that, you're still looking at the original 10-dimensional space that you formulated your string theory in.
Okay. Yeah, that's beside the discussion.
Okay. So, starting at the last week of the semester and working backwards.
I'm happy I didn't say it.
Okay. Let's see. We sort of breezed through Hamiltonian mechanics. I asked you to read about the Hamilton-Jacobi equation. I'm revising my notes in my classical mechanics course, but that'll be online, and that goes into much more detail than we should take the time here to go through. So, unless we need to go back and review some element of canonical quantization, I don't think we really need to go into Hamiltonian mechanics. Let me review. Let's see, what was I starting to write here? Yeah, just review the sorts of things that we will need. There goes our string theory. All right, so this Lagrangian is a function of the positions and the velocities. Like this, possibly time, though not usually explicitly time. And we can define a momentum conjugate to the coordinates by taking the partial of the Lagrangian with respect to the velocities. Then we define the Hamiltonian, give or take a sign, as a Legendre transformation that replaces the velocity dependence of the Lagrangian with momentum dependence. And we showed explicitly that happens, that this Hamiltonian is then depends on the momentum and the coordinates, not on the velocities. Let's see, so what happens in field theory? Let me take just a minute to talk about, let's see. No, let me continue this review.
Is there a time component in there still? Or?
Well, of course, everything we do is going to be relativistic.
Yeah.
So, it'll be space-time coordinates here.
Mm-hmm.
And the dot on the Q, well, the Q is actually going to be a field.
Mm-hmm.
So I want to get to this, but we end up writing the Lagrangian as the integral of a Lagrange density. So we're going to have some spatial integral of a Lagrange density built out of the fields and their derivatives, whatever fields we have.
Okay.
D3x.
Starting off.
Right. So we're going to need to take a partial to find the conjugate momentum here. What we need to do is we do the same thing. We take the partial of the Lagrangian with respect to phi dot, which is one of those derivatives.
Yes.
But the Lagrangian itself is a functional of the fields, and so this becomes a functional derivative. And I'll teach you what that is. We'll go over what a functional derivative is. Okay. It's a lot like a regular derivative. In fact, there are technical things that you can clean up nicely, but basically you just pretend you're taking partial derivatives. You forge ahead. So you need the functional derivative of that. But
now
that's basically the only difference between canonical quantization of mechanics, point particles, and canonical quantization of fields.
Now for that thing, if you have like your Lagrangian density as a function of like higher order derivatives, you have to take those also in your kind of thing that you did there?
Well, not to find the conjugate momentum.
Mm-hmm.
It would come into your field equations, sure.
Yeah, but
sure.
Not into the momentum, because the momentum would just be the
have you done that with Lagrangians? If it depends on Q double dot, say?
I've seen it. I haven't done it.
You need to do two integrations by parts to separate out the del Q and get the generalization of the Euler-Lagrange equation.
Yeah.
It's straightforward.
Mm-hmm.
It's straightforward. We could look at that sometime.
So, question.
I probably did it in the on the classical mechanics page where I've linked
Mhm.
the book Not So Classical Mechanics.
Yeah.
I do it in there.
Okay.
It's in there. Yeah. Sorry.
You're saying that the process of taking a functional derivative amounts to quantizing the.
No. It's, not to quantize. This is just right. Field theory has a classical Hamiltonian formulation.
Oh, okay. Yeah, because this.
So this is how we would do that.
Right.
What I'm starting to set out for you is how we proceed from this to canonical quantization.
Okay.
So we can get Hamilton's equations of motion, right? The time rate of change of the coordinates is given by the Poisson bracket of the Hamiltonian with the coordinates, and time rate of change of the momenta by the Poisson bracket of the Hamiltonian with momentum. There's no explicit time dependence of the coordinates in the phase space, of course. So now we find all this, and we do the same thing in field theory if we want to quantize it. Then what we do is we impose some simple rules. What we're going to do is take the coordinates and the momenta, and we're going to make them operators. And to make them operators, it's very hard. We put a hat on them. You're an operator.
Right. Well,
Okay. So if it's got a hat on it, it's an operator. Now,
what kind of
what on earth
operator?
does that mean? This
Right.
is exactly the question I wanted. One of the two real questions I want to address today.
Okay.
So we will get to what I mean by an operator.
Because in garden variety quantum mechanics, because we work in Hilbert space, these self-adjoint operators on Hilbert space.
The Python called.
Exactly. So, well, you've just answered the question. What we need to do is introduce the Hilbert space. So the operators are linear operators on some Hilbert space. So that's what I mean by the hat. The thing we didn't do when I gave these three rules. Okay, so dynamical variables. All right, so we have a dynamical variable is just any function of the canonical coordinates in time. These are going to be replaced by operators as well that depend on x and p and t. Where in general we define these by the old function evaluated at, using the operators. So we just put the operators in the function, and that makes f an operator. And this is what we got up to last time. This is the basic procedure for canonical quantization. Now, we've just pointed to one thing that it overlooks. There are two. There are two things we need to clarify about this. The first and most important is, what do we mean by these operators? The second is that this is not a unique prescription. For example, suppose f is the function x dot p. Well, that's the same as the function p dot x, and so we don't worry about ordering. But as operators, x hat dot p is not the same as p hat dot x.
Right.
Aren't they anti-symmetric?
Aren't what anti-symmetric?
Like
Dot products are
X
symmetric, but
no, the one that you just wrote that's not equal. Isn't it like minus I h bar it equals or something?
well,
like it's
sure. Okay, let me do one dimension to make it trivial. So if I've got x hat p hat, then suppose I have alpha x hat p hat plus beta p hat x hat in my Lagrange, in my Hamiltonian or something. Okay, I can rewrite one of these. This is the same as alpha x hat P hat, actually alpha plus beta, X hat P hat, plus beta times the commutator of P with X.
Mhm.
Right, well, the commutator of P with X is, let's see, minus I H bar.
Yeah.
There'd be a
And then-
chronometer if we were in 3 dimensions.
Sure.
But,
Oh, yeah.
just times 1. So in fact, I can write this as alpha plus beta
Mhm.
X hat P hat.
Yeah.
And if that's what I choose, always put the P hat second. Minus I H bar beta. So I pick up a term if I, shuffle the things to some particular order.
Gotcha.
The question is, well, is there some order I want? This is an ambiguity of the canonical quantization procedure, right? I could write either of those or some linear combination of them, and there's nothing about classical mechanics that tells me that there should be any difference, and yet quantum mechanics, like we know there is. So what do we do? What we actually do is going to wait until we quantize the scalar field, which I think, did you guys quantize the scalar field in Dr. Torrey's presentation?
Yeah.
Did you work through that? What did you actually ever quantize?
we quantized, I guess, the electromagnetic field.
Yeah, you were looking at photons, so
Right. So
you
we
would've-
came out with like the vector potential turned into an operator, right?
So, yeah,
Written in terms of like the integral of these field operators.
yeah.
Yeah. So
Yeah.
so we did that sort of thing.
Yeah, in that case, let's see. Well, with the electromagnetic quantization, I don't think you run into operator ordering issues. With a scalar field, no, you do. Sorry. If you write the Hamiltonian,
Okay.
right? Let me answer the questions in order. Do you know, first, these operators, what are they? We need to introduce a space of states.
Oh,
Yeah. So let me talk about that, and then we'll come back to the operator ordering.
right.
Okay.
It's on video.
Okay. Because okay, so we know that there are a number of operators we can write, any dynamical variables, so any functions of our x hat and p hat, and we know what they are in the sense that we're going to allow them to act on some Hilbert space. Okay, we require a Hilbert space.
Yes.
It's just like an infinite dimensional vector space.
It's
Well,
not necessarily infinite.
Okay, this is correct. So the first thing is it's a vector space.
You need completeness. You need.
All right, it may be an infinite dimensional one. It could be a function space. When we write the Schrodinger equation, psi is a function. That's an element of a function space. Now, you said completeness, right? It has to be complete. Can you tell me what it means?
Let me recollect. Completeness has something to do with. Oh man, I'm freezing.
Take a Cauchy sequence.
Oh yeah. So you have to have. Well, this. I guess this could be complex. This could be a complex.
Yeah, these are probably complex, yes.
Okay, so for
So,
real
yeah,
numbers.
let's in fact say that. Because it generally is. Okay, complete. So go ahead. So suppose we have a sequence of states in the space. Then
the all Cauchy sequences in that space converge.
So the limit of this is, and goes off to infinity, is some psi that is an element of our Hilbert space.
Yeah.
Okay, so Cauchy sequences, convergence sequences. So if we have psi n minus psi m, or
It's to be less less than some
yeah,
epsilon.
that we can find m and n, right,
Right. Greater than
such that
that is
yeah.
sure.
So yeah, any n and m greater than some capital N.
Yeah.
The difference between these is as small as we like.
Actually, here was the question that at the time Dr. Torrey talked about this, I wasn't up to speed. But recently
Yeah.
I realized that what it means to be a Cauchy sequence is to be able to, it's like all converging sequences are Cauchy sequences. So it seems to me that it is redundant that we say that in our Hilbert space, we need all Cauchy sequences to be converging. Well, they're converging by definition.
Oh, converging to an element of the vector space.
Oh.
It may
I
converge to something, but it may not be in your space.
Oh, I see. I see.
That's the real issue. So that makes it complete. If the limit vector of every Cauchy sequence is a vector in the space.
Ah,
Now there's something I've already
That's-
written on the board that we haven't put up as a property though. What does this mean?
The square margin. No, that's not the square margin. Actually,
Well,
That-
sort of.
yeah,
What is it?
the,
Yeah, we need a norm on states. We need some kind of.
yeah.
normalization.
Okay, now
Orthonormality.
if we only ask for a norm,
Uh-huh.
okay, which takes one of our states with its dual in some sensible sense.
It doesn't necessarily
and,
have to be one.
gives us some positive real number. That doesn't make it a Hilbert space.
Mhm.
This makes it a Banach space.
Okay. So Hilbert space is one extra constraint on a Banach space.
You need an inner product.
Less. Yeah?
Inner product.
Less. Banach spaces are like the higher category.
Yeah.
Right?
Mhm.
It's a bigger
Yeah.
group, a bigger set of things. Hilbert space is an inner product space. So this is an aside here.
Yeah.
We need an inner product space to make it a Hilbert space. So we can take any two states and have that be some complex number.
What was that?
Complex number.
And then doesn't have to be orthogonal also in Hilbert space.
Well, there may be a notion of orthogonality.
Yeah, because usually if you take like the one that you wrote there, like psi on psi, you'll get that to be 1, and then like psi on psi 2,
Well,
something
okay,
there
now
in a basis.
the norm of this isn't 1 until we're allowed to, until we have a dynamical equation. Right? We're eventually going to write the Schrodinger equation.
Yeah.
So the time evolution of a state is given by the action of the Hamiltonian operator. Okay, now that's a dynamical equation that governs the evolution of states. And okay, now we notice that if I replace my states by a e to the I phi times the state, this relationship doesn't care. Right? It's conformally invariant, complex conformally invariant, in fact.
Well, doesn't that
Now, there's a
Doesn't
real
that
amplitude in the
depend
phase.
on your Hamiltonian operator though? If you have some time dependence on some potential in your
No, this
Schrodinger
isn't
equation.
time dependent. I'm just multiplying by a real factor and a phase.
Mhm.
This is the unitary invariance of the theory, the phase. That's the normalization.
Mhm.
So because we're actually talking about equivalence classes of states, for all A and phi real, So our equation, our dynamical equation applies to equivalence classes of states. And we're free to choose any representative of that equivalence class. So our states can be multiplied by a constant phase, and it doesn't change that it's the solution to the Schrödinger equation. We can normalize our states to 1 using the real amplitude there. Question?
I've heard the term ray. Is that a ray?
That is a ray. Yes.
That's the.
Yes, a complex ray, but yeah, that's right. Yeah, so to form a ray, if you take a direction in a space and you look at just all multiples of that, often R plus, so you get every vector in that direction. It's really the direction of a vector in Hilbert space that has the physical content.
Right.
So yes, that is a ray. Okay.
For completeness, like the definition that I remember seeing was if you had some state, let's call it, chi, then you can break it into, some summation, call it an infinite summation of, these coefficients of their probability and all these other states in your basis. We call it basis psi or something.
Well, yeah, let me talk about that a bit.
Mm-hmm.
That's sort of the
Because
next thing up here.
The sequence things, I haven't seen that before. So.
I feel like there are two separate things in his question.
Okay. What do you want to...
One, so there is this notion of having your operators span the whole Hilbert space.
Yeah.
In which case they can act as a basis, right? There is like a problem last semester you helped me with where we put, I think it was like a
so a basis for states.
Right. So in which case you could define orthonormality.
Mm-hmm.
Oh yeah. Okay.
But he is also talking about completeness in terms of a sequence that he saw. Yeah, completeness defined in terms of these. What I'm thinking is the Cauchy sequence.
So the Cauchy sequences are what define completeness. The space has to be closed under Cauchy completion.
Right.
And we need our inner product to evaluate that. And then it works, right?
Right.
For the function spaces you're used to, it works.
But it's as if Josh is saying that if that property is fulfilled, you could define. Josh, ask your question again.
There should be like an extra thing that should happen if it's much easier if I just write it up here. That if I'm given some state, let's call it chi, and I have my basis, and I'm complete, which is just a requirement of that, I should be able to expand this and, some summation like this, call it n equals 0, for some, completeness coefficient, call it an.
Well, you're simply defining a vector space.
Like
right.
psi and like that. Yeah, where you could take like, psi
It is certainly the case
and then that should be
that every finite dimensional vector space has an orthonormal basis.
Yeah.
Right.
And then you have like that, 0.
Yes, we can ask whether there exists an orthonormal basis for our Hilbert space.
Yeah.
If it's finite dimensional, unquestionably the answer is yes.
Yeah.
In fact, if it's infinite dimensional, the answer is still yes.
Yeah.
Right. We have that, and I'm going to define a couple. So, what we know as theorems from quantum mechanics is that Hermitian operators have a complete set of eigenvectors with real eigenvalues. This is the reason we use Hermitian operators to describe physical observables
Because they're all measurable.
Because they're measurable because their eigenvalues are real.
Yeah.
Okay, so we can find a couple examples because we have some Hermitian operators. We have the position operators. So we can immediately define some states. Let me use a vector hat notation here. And right, so the difference here, that's a number, that's an operator. And it's going to pull out those three real numbers. So I'm going to label the eigenkets of this Hermitian operator by a set of positions, the eigenvalues. And now we know that these form a complete set of states. But now here's the thing that happens with orthonormality, right? How do you do that when you have a continuum, an infinite continuum of states, right? Well, what you have for the completeness relation, what it means for this basis to be complete is that, as you suggested, every ket, every state, can be expanded. Well, certainly I can let the identity operator act on that. And let's think a bit about what the identity operator looks like. In three-dimensional real Euclidean space, right, we have basis vectors. We could take I cross I plus j cross j in this dyadic notation, and that would be the identity. You see, basically I cross j would be an off-diagonal element. So some ones times the diagonal elements is the identity. Now, in bracket notation, we would write this as, we would write this one going that way and that one going this way.
So like you have a projection
So
operator.
the sum of these things, so the sum of the outer product of your basis vectors is the identity. Right?
Yeah.
So if those are orthogonal states, then, well, let's see. If they're orthonormal states, this is what we expect. We expect to be able to write the identity operator as the outer product of a bunch of orthonormal states. So let's use our freedom to rescale to make these states orthonormal. But
And
we have to know what that means.
Where do you get the freedom from to be able to do that?
From the Schrodinger equation.
Okay.
The Schrodinger equation doesn't care if you multiply your state by a
By a
complex
to the
number.
I. Okay. All right.
Right?
Yeah.
So here, I'm going to write this as a sum over all the states, but hey, wait a minute. I have a continuum, so it's got to be an integral. So this is what my identity operator should look like.
Gotcha.
Now acting on the state psi. These are your coefficients.
Mhm.
That's also the wave function. That's a real number of psi of x, or complex number of psi of x.
Yeah.
Right. So the coefficients in the expansion in the coordinate basis are just the wave function at each position. You see here.
Okay.
Okay. Now the
I have one other quick question.
I'm not done here. The completeness relation. Let's see. It tells us that if I bring an x prime into this psi, what am I going to get? I've got d3x, then I've got x prime x, and I've got x psi here. But in order for that to be true, what does that inner product have to be?
1.
Won't do it. It'll be infinite.
Oh, it'll be.
Well, it would be the integral of the wave function over all space. And it won't depend on x prime.
Delta function.
Oh.
Thank you. Yes, that's right. You want this to be a Dirac delta.
Oh, so you're switching it to momentum space now, if you have
No, you're getting ahead of it. Go read Sakura. Okay, all of this is in Sakura. Okay, so the orthogonality relation for a continuum basis is a three-dimensional delta function in this case. It's about 6. Like that. We can also have discrete bases for a system. The set of states depends on the solution set, some subset of Hilbert space. But it depends on the Hamiltonian. So you know perfectly well the solution for the simple harmonic oscillator
Right.
is a set of discrete states with energy given by h bar omega n plus a half times n. All right, so we have a countable infinity of states. We can also put those states, write them as a wave function, put them in a coordinate basis, and they're Hermite polynomials times Gaussians. So the states can be written either way, in a function space or in a discrete Hilbert space.
Joshua, what was your quick question?
So a Hilbert space doesn't necessarily prescribe that your completeness is, orthonormal. It doesn't necessarily say your basis is orthonormal.
You can have a non-orthonormal basis.
Okay, all right.
The criterion for a basis is that every state needs to be expressible in terms of it as a linear superposition.
Yeah.
That's the property you need. Normalizability, by the way, for the expression you've written here,
Yeah.
right? If we want this state to be normalized, then we take two series like this, and what we're going to get when we sum them is the sum. We'll have a sum on m and n, but then we get a Kronecker here.
Yeah.
We'll end up with the norm of those complex coefficients here.
Yeah.
Summed. So that has to be 1. That's a constraint on what those coefficients can be.
Yeah. Gotcha.
Okay. Good. All right. So passing. There's a whole lot of this in Sakurai. And in my quantum notes, if you want to look at those, that's really the main content of the first.
Yeah, I recently went through your quantum. That's why I remember this.
Yeah. Okay. Yeah, the first 2 or 3 chapters of Sakurai deal with all of this kind of notation, and you'll find it in my notes too. Okay. So, and I talked about having to go to functional derivatives when we apply this to fields rather than to just particles. Now, let's talk a little about operator ordering. I guess we did sort of talk about operator ordering, didn't we? There's an ordering ambiguity. Let me give one little instance, though, of what happens. Let's look at the simple harmonic oscillator.
Can you say that identity term that you wrote there for just a second?
Yeah, sure. I'll start over here.
Awesome.
So you've all solved the simple harmonic oscillator, quantum simple harmonic oscillator.
No.
Have you?
It's been a while, but
It's been a while. Did you define the raising and lowering operators?
Yeah.
Right. I'll write the definition. So you have your position and momentum operators for the one dimension. I mean, let's do just one dimension here, maybe. No, let's do 3. We can do 3. Okay, so we've got our position operator, our momentum operator, and we can define some other operators, m omega over 2 h bar, and xi, and this would be plus I over.
Right. So I is posing for 2 jobs in this equation.
Oh, is it? Oh.
That's
well,
that's fine. You can.
Yeah.
1, 2, 3.
Yeah.
Okay, yeah. I'll try to make my indices float.
Yeah.
I don't think we'll run into much trouble.
Yeah.
Okay. Now, notice that this is not a restriction operator, so we can't go out and observe these. The dagger, remember that X and P are Hermitian, so all that's going to change is this relative sign.
So you're just taking the Hermitian conjugate.
Just take the Hermitian conjugate of that and you get this.
Yeah, gotcha.
Now, we can work out the commutation relations of these. That's not so hard, so let's do it. AI dagger with a J. We're going to have two factors of that square root, so this factor comes out front. And then we have the commutator of x hat minus I over m omega p hat with xj minus plus I over m omega pj hat.
And this, just to refresh my memory on this, that Hamiltonian right there that's the harmonic oscillator Hamiltonian, spitting out the harmonic oscillator.
Those are
If you-
eigenstates of
Eigen-
the Hamiltonian.
Gotcha. Okay.
Right.
All right.
The Hamiltonian is actually, can I erase here now?
Yes.
The Hamiltonian for this system comes from the simple harmonic oscillator Hamiltonian,
Okay.
which is just the total energy, 1/2
Mhm.
M X dot.
let's
Wait,
see,
wait,
well,
depends on
let's say p squared over 2m.
Yeah. Depends on where you want to
plus
start.
1/2 k x squared.
Sure.
And I define omega to be the square root of k over m.
Yeah.
Yeah.
Okay.
So I can write that in terms of omega. Right. But
Just
then
like this.
the operator, now let's ask, do we run into any ordering ambiguities? No,
Mhm.
because I just have p's and x's separated nicely.
Mhm.
Let's see, so k is going to be what, m omega squared, right? So 1/2 m omega squared
Yes.
x hat
Right.
squared. So this is the Hamiltonian.
Gotcha.
Right.
Mhm.
What we do though is we write it in terms of the A and the A dagger. Now X commutes with X, P commutes with P, so I'm going to, the only terms that survive will have an I over M omega, where that I is really an I. And then we have X commutator P minus P commutator xj, like this. And let's see, we probably know what those are. I probably wrote down what they are. Let's see, x with p is minus I h bar. So this is minus I h bar, this is I h bar. So we're going to get minus 2 I h bar. The 2 cancels, the h bar cancels.
And
This
then
m omega cancels and we just get 1.
the I will.
The I and the minus I here
Yeah.
give 1. So this just ends up being a Kronecker, delta ij.
Gotcha.
Should have written those up. Okay, so very simple commutation relation for these, and of course they each commute with themselves. All the A's commute with the A's, all the A daggers commute with the A daggers.
Now, for the AIs that you wrote above, should those indices be up too?
Yeah.
Okay. Not to be stickler, I'm just.
Yeah, you know, it's important to do it right.
Okay.
So, question? Yeah, good. Okay, everybody good here? Okay, now, if we write the Hamiltonian in terms of these, let's see, well, just invert these relationships and substitute into here, and you will find h bar omega times
A
quantity A hat I dagger A hat I plus 3 halves. And you're wondering why it says 3 halves.
Yeah, I don't remember the 3 halves.
That's because you did it in 1 dimension, not 3.
Oh, okay, okay.
So
good.
each degree of freedom you get an additional
Just
1
like-
half.
Equal partition type theorem.
Yeah, that's right. That's right. Okay, so yeah, there's that surprising thing, but it's nicely indicative of the real point I want to make here. what happens in quantum field theory. Now, you guys have actually done this expansion where you expanded the vector potential, I believe. Did you write as an operator? When you solve the
Yes, we
vacuum E&M equations,
Yeah.
you have some amplitudes here.
Yeah. So we wrote those as epsilons or whatever.
These guys.
Oh,
well,
so-
there's an epsilon as well, right?
Yeah.
So that's the polarization, and then you have.
The A's and A daggers.
So yeah, you have a polarization vector. You have an A that can depend on polarization and wave number. Operator e to the I k dot x minus omega of k t plus the Hermitian conjugate of the whole thing to make it real. And the commutation relations, right, this involves an A dagger, and the commutation relationships of those, epsilon k with A, which way did I write it? Dagger first. A epsilon prime k prime 3 vector k. What does that equal to? Well, you have to have the same polarization states. You need a Dirac delta function k minus k prime. But otherwise, okay, that's good. Those satisfy that kind of commutation relationship. So what you're looking at when you look at this expansion for the quantum vector potential is a superposition over d3k, a summation over polarizations.
And there was like a 1 over 2 pi.
There are coefficients.
Yeah.
And we're going to get back to this when we're really going to quantize that.
Right.
So we'll see that again. But the point I want to make here is what is this constant for E&M? How many degrees of freedom do you have?
When looking at.
We've got 2 here. And then we're integrating from minus infinity to infinity 3 times, so we get infinity cubed. This constant becomes rather large. That's divergent, right? The vacuum energy. You have an infinite number of modes, a triply infinite number of modes here. Every wave vector k has a mode. Every wave vector k gives you a possible vacuum energy. So this constant diverges. And this is where we use our freedom to order operators. We introduce what's called normal ordering. This is the first infinity we hit when we start doing quantum field theory. And we can get rid of it simply.
For the Hamiltonian operator up there, that just equals that h bar omega. Raising lower. Okay.
This is the Hamiltonian for the
Gotcha.
three-dimensional simple harmonic oscillator, quantum simple harmonic oscillator.
Gotcha.
Yeah, 3D QSHO. There you go. That's what it's called.
Awesome.
Yeah. Normal ordering is denoted by enclosing things in a pair of colons. The normal ordering of an operator in this space means, right? It's really defined to be putting all annihilation operators to the right of all creation operators.
Mm-hmm.
If you do that way back when you start to construct the Hamiltonian, all right, as you start to construct this in terms of you get both terms. You get an A dagger A times some stuff, and you get similar stuff times an A dagger.
Yes.
Right? So your Hamiltonian works out to be of that form, but the normal ordered Hamiltonian just gives you 2 of the first one. Because you put the A to the right. That's the order you use. Always put the annihilation operators to the right. And that means you don't have to commute this and pick up that factor.
Is that why the number operator is defined in terms of, I think it's A dagger.
No, the number operator is this because the eigenstates of this Hamiltonian, back to the 3D QSHO, this Hamiltonian acting, we can find operators n such that you get h bar omega n plus 3 halves, where n is the eigenvalue of this. So you diagonalize it in the AA dagger space. So we do define an operator n hat to be a
dagger A.
And you sum over those because you're going to pick up all of them. And you'll find that always returns that number in. So these are simultaneously diagonal.
So meaning Professor Torrey took care of this, and that's why we never noticed it.
He did the normal ordering.
Yeah.
So he just, the normal ordered one
We
is
never got into that.
just well, let's normal order the one that comes from field theory. We're going to have D3K, sum over polarizations, and we're just going to have a dagger. So you don't get an additive constant here because you have normal ordered the Hamiltonian. You're allowed to do this. This is a freedom that happens when you go to quantized systems, right? We haven't cheated here. What we've done is choose the one way of ordering our operators that doesn't run into conflict with the vacuum energy.
Question.
Yeah.
Is this now quantized?
Oh, pretty much. Yeah. Now, we didn't go through the quantization, right?
Okay.
So what do we do to quantize electromagnetism? Where do we get this expansion?
That's a solution to Maxwell's equation.
Exactly. We solve the vacuum Maxwell equations.
Yeah.
We do it in the Hamiltonian picture, so we also solve for the conjugate momentum. Or we know how to compute the conjugate momentum from this. It's just a derivative.
Right.
Right? And so we have commutation relations for A and its conjugate momentum pi. Right? So from the Poisson bracket of these, we multiply by I over h bar and get the commutator of these. And then from the Fourier series solution to the vacuum Maxwell equations, where we have now made these into operators, we can invert this equation and solve for the commutation relations of these. And they turn out to be just like just like this. You have to derive this.
Right.
That's going to take you a few days in your homework. You're going to do that. Right? And inverting, you have to invert a bunch of Fourier series.
Yeah.
Right? I mean, there's a real calculation to do there to prove all these results. And judging from where we are and the kinds of questions, maybe it's better to do that sooner rather than later, since you have already seen the quantization. I wonder, I was working up, I was trying to come up with a really brief way to go from particle Lagrangian to a field Lagrangian, to see how you get continuum equations of motion, or a continuum Lagrangian. Let me try to do that, but it involves a little bit of hand waving because I'm trying to simplify it enough that I can say it in a short amount of time. You can expand everything carefully, but unless you make some radical approximations, you end up with a wave equation for a vector field rather than for a scalar field. And really, we'd just like to see some kind of scalar field Lagrangian emerge. So let me just talk through that and see if I can
How does
finish
this
that up today.
simple ordering thing work?
Mhm.
Because like if you switch those things, don't you have to pick up that the
No, this is the point. You do not commute them. You normal order them.
okay.
All right. So let me say that explicitly. All right. So okay. So A dagger A plus A dagger is equal to let's say A dagger A plus the commutator of A with A dagger. And what is that, plus or minus? Right. Let's see, A dagger A is plus, so that's minus. So this is minus 1, right? So this is equal to A dagger A minus 1. Right. Now, A dagger A plus A dagger. Oh, I'm sorry, two of these. Two of these, and then I added and subtracted one of those to make this a commutator. Okay. Now I put colons around this. That is twice A dagger A. Period. That's what it means. So it means put that on that side. Period. Don't commute them.
Okay.
It's just that's what the colons mean. It's just one more rule that uses our freedom to order operators.
So are you doing like an operation on that thing then?
Yeah, the dot thing is just some kind of operation. It turns that into that. Well, now, this doesn't work for just anything. I mean,
Yeah.
Given that this is the rule you apply to creation and annihilation operators, what does that do to P and X? Is there some ordering of P and X that will do that? It's not obvious that there is. I mean, try and find one by all means, but I've played around with that. It's not just simple to see what rule this implies for P and X. But if you can expand your theory in a Fourier series with creation and annihilation operators for the operator coefficients, then you know what a creation and annihilation operator is, and you can define normal order. That's fine if you have a linear field theory. General relativity is not. So, the space of states, the vacuum energy, all those kinds of questions for general relativity are more difficult.
So we used our freedom in the Schrodinger equation basically to add one.
In this case, it's adding one, yeah.
Okay.
If I had two here, then I would end up with 3 of these and 2 of those, so I'd be subtracting 2 and getting 3. Right? I mean, it depends on what this thing is. But the normal ordering of that is then 3 of these.
So you're just like imposing commutivity basically on the thing.
Yeah, it's
kind of what
not.
I'm
It is not
saying.
a commutator. I'm changing the order of the operators by fiat.
By phi hat?
Yeah. Yeah.
What's phi hat?
it's,
I'm sorry. I just
it's a car. Listen, no, it's
like
yeah.
say a lot more.
It's just out of hand. I'm just doing it.
Okay, so you're defining that.
Yeah,
that thing to
that's
me.
the definition, right?
Okay.
That's what I mean. Put all annihilation operators to the right of all creation operators.
Okay.
Put them there. Just put them there. Okay. Let's see. I don't know. Is this another cows come home day?
I need to go in a couple minutes.
You need to do okay. So I'll put this off till next time. Maybe I can tune it up a little bit. I'll do a brief thing of getting a continuum field theory out of a particle theory by taking a limit, a continuum limit. And let me see, what's coming up next?
It looks like, according to your book, it was
Some things in quantum field theory, looking a little bit at